So let's talk about sequences. All a sequence is a list of numbers in a special order. One of the most well-known sequences is called the Fibonacci sequence, and you might have heard of it. And this one is awesome because it's seen in nature all the time, and it's just kind of the ratio here. So this pattern that we see in a snail is an example of the Fibonacci sequence. And the way this one works is you just add the previous term. So 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, and so on. So we add them up to get to the next term. Another well-known sequence is a geometric sequence, which you might have heard of before. And this is really relevant to you because this has to do with how credit cards work and mortgages for your house payments and things like that. So in this example, let's say you charged $350 to your credit card and decided that you weren't going to pay that off for 3 months, okay? So I calculated this at an interest rate of 18%, and we'll talk about this more later. But basically what would happen is if you started with $350, the next month you would have to pay $413, and then the third month, if that's when you decided to pay it off, it would be $487.34. So that interest is accumulating, and that's a type of sequence. So let's get into some of the vocab associated with sequences. So these 3 little dots here at the end of my Fibonacci sequence indicate that this sequence is continuing forever. So what we say is this is an infinite sequence. If your sequence doesn't continue, then this would just be a finite sequence. Okay, and I could have made this one an infinite sequence had I decided it would go on longer forever. Okay, but hopefully we're not accumulating interest forever on our credit cards. That would not be good. So finite and infinite. And then as far as notation goes, we use what's called U sub n, and this represents a term in the sequence, and n is the position of that term. So for example, if in my Fibonacci sequence, I wanted to find U sub 4, what this is asking for is what is the value of the 4th term. So I would look up here, this is my first term, second term, third term, 4th term. So U sub 4 would be equal to 3 in my Fibonacci sequence. Okay. If I said U sub 6, then we would look for our 6th term over here. So 1, 2, 3, 4, 5, 6. So it would be equal to 8. So that's going to just be some important notation stuff for you guys to use going forward. And what we're going to do next is use equations to represent our sequences. In the next video, we're going to get into some specific types of sequences and how to solve those in particular. But right now I want us to look at sequences kind of like a puzzle and see if we can come up with an equation to represent the situation that we see. So let's start with this first example. Hopefully these numbers look very familiar to you, right? We have 1, 4, 9, and 16. These are all perfect squares. So I could write 1. 1 is the same as just 1 squared. 4 is 2 squared. 9, 3 squared, right? And 4 squared. So if I wanted to write an equation to represent this, we're going to use U sub n. And n is the position, right? So if this is the first term and it's 1 squared, and this is the second term and it's 2 squared, then the way this equation would work is it's just whatever position it is squared. And that's it. Okay, so this would work for perfect cubes or anything like that. So let's look at our second set of numbers. Here, these don't automatically jump out at me as any special type of number. So we're going to see if we can think of any mathy way that we're getting from the first number to the next number. So let's try just addition and subtraction. If I start with 2 and I add 7, that gets me to 9. And then 9 plus 7 gets me to 16. And just to verify, 16 plus 7 gets me to 23. So the rule that's happening here is we're adding 7 each time. And this is actually called an arithmetic sequence, which we'll get to later on. But let's explore how to write this as an equation. So I know I'm going to start with U sub n. My first term, I'm going to make a little table. My first term is equal to 2. And then for my second term, I did 2 plus 7. My third term, I did the 2 plus 7, and then I added another 7, right? And then my fourth term, I had the third term plus another 7. So what's going on here? An easier way we could write this, right? Instead of 7 plus 7 plus 7 plus 7 plus 7, this is the same thing as 7 times 1. This would be 7 times 2. This would be 7 times 3, right? So my fifth term, I would expect to be 2 plus 7 times 4. So we need to figure out how to put this in an equation now. So I know that there's 2 plus 7, but how do we get to these numbers using n? So if we look at the relationship, right, when I have my second term, I'm multiplying 7 by 1. When I have my third term, I'm multiplying 7 by 2. So each time, I'm multiplying by 1 less than the actual term. So I'm going to put n minus 1. Okay, so this does require some thinking. And like I said, we'll get into a more specific way to do this, but just so we can kind of understand the basics and have to think a little bit. Okay, let's see if we can figure out this next one. So on here, I'm going to start with just the numerators, okay? So the numerators, my first term is 1, my second term is 2, third term is 3. That looks pretty easy. So un equals, and just in the numerator part, it's just whatever term it is. First term, second term, third term, fourth term. Now the bottom part, you should see pretty quickly that each denominator is going up by 2. So take a second, this is really similar to the last one we did. See if you can find a way to express that as an equation. Okay, so just like before, my first term is 3. My second term is 3 plus 2. My third term is 3 plus 2 plus 2. So the way we would do this is 3 plus 2, and again times n minus 1. And that would be my equation. Sometimes we have sequences that aren't as easily written as an equation. And what we do is sometimes we can use what's called a recursive sequence. A recursive sequence is when we use the previous term to come up with the next term. So an example of that I gave before is the Fibonacci sequence. And the way that one works is to find your term, you add the two terms before it. So 1 plus 1 equaled 2, and then 1 plus 2 is equal to 3, and so forth. So the way we would represent this is using previous terms. So if I want to find any term, I'm adding the two terms that come before it. So the way I write that would be, I would take 1 less than my previous term plus 2 less than my previous term. So let's kind of put this in context. So for my Fibonacci sequence, if I wanted to find the sixth term, which we see right here is 1, 2, 3, 4, 5, 6. So this term right here, I would then take my n minus 1, so 6 minus 1 plus 6 minus 2. So my sixth term would be equal to my fifth term plus my fourth term. And if we plug that in, we can see up here, that means that 8 should have been equal to my fifth term, which is 5, plus my fourth term, which is 3, and that is exactly correct. So we can use this notation. It's just called a recursive sequence instead. So let's look at another example. So for this one, the first thing is we're going to try to identify our pattern and try to see what's going on. So I always like to start by looking for addition, subtraction, or multiplication, division. Addition and subtraction don't work, but multiplication does. So 3 times 4 is 12, and then 12 times 4 is 48. So that's my rule. And I can actually write this as a general formula, but if I specifically asked for the recursive formula, we can do that too. So the way this would work is I'm always multiplying my previous term by 4 to get the next term in the sequence. So to get any term, I'm going to do 4 times whatever the previous term is. And again, to do the previous term, it's whatever term I'm on minus 1. So again, to see this in action, if I wanted to find my third term, it would just be 4 times 3 minus 1 is 2. So 4 times my second term. So I'm going to look up here. My second term is 12. So this would be 4 times 12, which is 48, as it should be. Okay, the problem with recursive is that you need to know the previous term. So if I wanted to find in this same sequence the 8th term, I'm going to need to know what the 7th term is, which means that I have to go back and count this out for every single one until I get to the 7th term. So that's the problem with recursive. We'd like to avoid it if we can, but sometimes recursive is the only way we can represent a sequence. In this video, you learned how to find the definition of a sequence, how to write a general formula using proper notation, which is our U sub n, and how to write a recursive formula using things like U sub n minus 1. Thanks for watching.